Alrighty, let's have a look at this double integral. Now it's a bit different to the previous ones we've looked at because the region of integration is just specified as D and the area element is specified as A. Now, of course, we're going to adopt Cartesian coordinates, but we do want to work out what the best order in which to do this integral is. So we're told that D is bounded by, that is, D is the region in between these two curves, and they're two curves that are parabolas. So y equals 2x squared and y equals 1 plus x squared. So let's firstly sketch these two parabolae. This one, 2x squared, is a fast-growing parabola with origin 0. So it starts at the origin and grows faster than this parabola, which doesn't have a 2 there, so it's steep. I know roughly what the answers should look like, so I'm trying to do my sketch to reflect that. All right, so there's 2x squared. Now let's do 1 plus x squared. Obviously, when x is 0, y is 1. And the parabola grows slowly. So we can imagine that somewhere along the lines we're going to intersect the other parabola. So the red line is 1 plus x squared. Okay, so when does that happen? So we want to find the x coordinate that this occurs at. So obviously, if they're to intersect, they must be equal. So the intersection occurs at 1 plus x squared equals 2x squared, yes? Because this is where the two curves are equal. We can rearrange this fairly comfortably. We subtract x squared from both sides. And so we see that x equals plus or minus 1. So we do find both of the intersection points, which is quite nice. And now we can comfortably shade in, shade in our region of integration. So it's this sort of big grin shape, I guess. We've now got to work out whether we integrate with respect to x first or with respect to y first. So let's just consider what happens if we try to integrate with respect to x first. So that is, we pick a y location and we integrate along horizontal lines. So that's going to work fine. We're going to be able to draw all these horizontal lines. Oops, too far. Up to this point. Right, past that point, we're going to get disjoint regions. Now, we could integrate with respect to x first, but we would have to split our integral into 3 separate regions. We would have to do one region here, another region here, and another region in here as well. So we'd have 3 different regions to try and deal with. So that's really not terribly practical. So we don't want to do that. We want to just do Because each of these regions, that's obviously, we've got an integral to do for each of them, and we don't want to do 3 integrals, especially not when we can just do 1 integral. So I'll just redraw my sketch very quickly. So obviously it looks like we're going to be integrating with respect to y first. Okay. So if we integrate with respect to y first, we pick an x value and we integrate upwards. Right, so this was 1 plus x squared. This is 2x squared. Those lines there. So obviously, if we integrate with respect to x first, we start at the line. Oh, sorry. With respect to y first, we start at the line 2x squared, and we stop at the line 1 plus x squared. So our integral becomes 2x squared is the bottom limit of our y, right? Because we can always do this, right? No matter where we go, we don't end up crossing any of these lines. Oops. Our integrand was x plus 2y, and we do the y integral first. Our x limit, we obviously start at -1 and we roll through until 1. So that's our integral, right? So our dA was dy dx, and there are limits that define the region of integration D. So let's just belt through this. This is a very simple integral to do because it's just a polynomial integrand. The limits are polynomials, so it's going to get, the x integral is going to get quite complex or complicated because we've got all those squareds floating around, but it's still a polynomial, so it's really not that bad. Integrate with respect to y. Remember that x is a constant, so we get that. We're going to get y squared on half times 2, so that factor's going to cancel out. The only difficulty here is going to be keeping track of all those squared terms, right? Because we're going to have to expand this out. Fortunately, I can just copy from the example that I did. Well, that someone else did actually. This example is from Stewart's calculus. So 4x fourth. Right, so you're going to have to blow that one up as well. But bits start canceling out. You get minus 3x fourth minus x cubed plus 2x squared plus x plus 1 dx. This is still just a polynomial in x, and they're easily integrated. Minus 3/5 x5 minus 1/4 x4 plus 2/3 x cubed plus 1/2 x squared plus x. Between -1 and 1, you plug all that in, you get 32/15. All right.